students, so we have seen the OR function. We've seen the OR gate. It looks like this. And we know that if we have inputs x and y, that x ORed with y is 0, 1, 1, 1 for our combination of inputs. Now I want to show you how to use Boolean algebra to do minimizations of logical functions that contain OR. So an example of a function would be something like x OR xy. So here we have a logical function that has two inputs, x and y, and x and y are being ANDed together, and that result is getting ORed with x. So we could make the logic diagram for this that would implement this function, but before we do that, it's a good idea to minimize the amount of gates that it takes in order to implement this logic. And a good way to do that is to use Boolean algebra. So let me show you the identities for the OR function. For a digital input x, so that means that x can be either 0 or 1. Let's let this plus sign be ORing. So it's not adding, it's not bitwise adding, it's actually the OR function. We have the following identities. All right, so we have that x OR 0 is equal to 0. Now, something interesting about this is this makes 0 the identity element for ORing, because we can sort of OR 0 with anything and we'll just get the original element back. The next one is that if we have x and we OR that with its inverse, we're always going to get 1. And that's because no matter what x is, if it's 0, then x naught will be 1. If x is 1, then x naught will be 0. So one of them is going to be 1. We know from this truth table that if we OR, if there's a 1 as any of these inputs, then we're always going to get a 1 on our output for OR. So the next one is, how about if we take x and we OR it with itself? So in this case, we're just going to get x. And this is going to help us with minimizing functions that have more than one literal. The next one is, if we OR something with 1, it doesn't matter what that something is. It can be 0 or it can be 1. If we OR it with 1, then our result will always be 1. Next we have, if we have the inverse of x, and we take the inverse of that, we're just going to get x back out again. And this is true for, this can kind of go under the OR identities or the AND identities. The next one is that if we have x OR y, that's equivalent to y OR x. And you may recognize this from algebra as commutativity. Commutativity. And it basically means that the order of ORing doesn't matter. Order doesn't matter. Okay, the next one we have is that if we have x ORed with y OR z, that's going to give you the same result as if you did x OR y first and took that result and ORed it with z. And you may recognize this as associativity. Associativity, and that basically means that the grouping doesn't matter. Okay, the next one that we have is if we have x and we AND that with y OR z, we can kind of distribute this x just like we did in regular algebra. Okay, so this is equivalent to x and y or x and z, and this one is distribution. And then the next one we have, and this one's important, I'm going to do a separate video just on this because we're going to use this quite a lot, and that is that if we have x OR y and we take the inverse of that, that's going to be equivalent to x naught ANDed with y naught. Okay, and this is called De Morgan's theorem. And we're going to use that a lot, especially when we're taking complements of functions. but more on that later. And the last one I want to tell you about is x or xy is equivalent to x. This is called absorption. And the way it works is if you had x or xy, and if we factored an x out of this left-hand side, we would get x times the quantity, right, and the quantity 1 or y. And we know from a previous identity that if we OR anything with 1, this is just going to be 1. So this thing here is just equal to 1. So that makes this x and 1, which is just equal to x. So these are the basic identities that we need to start with in order to do Boolean algebra on functions that have ORs in them. In the next video, I'll show you the same set of identities but for ANDing.